Okay everyone, this is going to be 4.6, the transformer chapter here. Look at the first question. A battery charger plugs into 230 AC volts supply. The charger is used to charge a 6 volt DC battery. The charger contains diodes and transformers. What is the purpose of these components here? Diodes are basically used to rectify AC. For those who do not know what rectify means, it means to say we're converting AC into DC. So rectification is this one. Transformer is obviously used to step down the voltage. So in this case here, A will be the answer. Right. Then moving on to the next question here. The diagram shows a transformer. The input is 240 volts. 240 volts here. Then after that, what is the output voltage here? It has 800 turns on the primary coil and 40 turns on the secondary coil here. So basically we're supposed to understand that here to here is a divide by 20, right? Yeah, it will be divided by 20. So here to here should be a divide by 20 as well, which is essentially going to be 12 volts. So B is going to be the answer here. Alright. Then after that, figure 8.1, 8.2 shows a DC power supply connected to a transformer. You're not supposed to connect DC here, but let's see what this question wants. When switch S is first closed, the needle of the galvanometer deflects briefly, then returns to zero. Explain why there is a brief deflection. Now, as soon as you connect this S switch here, right, what's going to happen is current is going to start to flow in this coil. This current will produce a magnetic field that cuts through the secondary coil once, and when it cuts through the secondary coil once, it will deflect momentarily, then return back to zero because the magnetic field is permanently stationary here. Electromagnetic induction cannot occur because the magnetic field is not cutting through the secondary coil. So basically they want you to explain all of this in terms of what you know. You're supposed to say that as the switch is closed, current flows from the DC supply to the coil, which generates a magnetic field that cuts through the secondary coil once. The galvanometer deflects due to the EMF produced and returns to zero because the magnetic field is stationary not cutting through the secondary coil anymore, right? There is no change in magnetic field basically. Okay, so this is essentially how you're supposed to answer this. Then moving on to the next part, figure 8.2 shows a transformer. A 240 volt mains supply is connected to the primary coil. The voltage across the secondary coil is 12 volts. So here is 12 volts, right? A lamp in series with a 3 ampere fuse is connected. The number of turns of coil is not shown. Predict with a suitable calculation whether the fuse blows when the current is 0.2 amperes on the primary coil. So here, if it is 0.2, what's going to happen is you have to understand that the ratio, since power is the same, right, for a transformer, it means to say if here in terms of the voltage is divided by 20, right, here to here the current will be a multiple of 20 because P is supposed to be equivalent to VI, right? And decrease in voltage is supposed to increase the current. So 0.2 times with 20 is probably going to give you 4 amperes, right? And if it is 4 amperes here, it's obviously going to cause the 3 ampere fuse to blow, right? So first and foremost, they ask you for a predictable calculation with suitable calculation, right? You're supposed to say that power in the primary coil is equivalent to power in the secondary coil, meaning to say voltage primary, current primary is equals to voltage secondary, current secondary here. So from here is essentially going to be 240 multiplied by 0.2 is equals to 12 multiplied by x, whereas your x would obviously be 4 amperes here. Since your current is 4 amperes, you're going to say that the fuse blows because 4 ampere exceeds the 3 ampere fuse. Okay, so this is what you're supposed to say. And moving on to the next exercise here, a straightforward one as well. The diagram shows a simple transformer with a 240 volt input and an output of 40 volts here. There are 600 turns here, right? They're asking you what are the number of turns in the secondary coil. Here to here is a divide of 6. So here to here should be a divide of 6 as well, which is essentially going to be 100 turns lah, right? You're supposed to get 100 turns here. Okay? Don't do this in your paper 4, by the way, just do it in the ABC question. A 100% efficient transformer has 6,000 turns on the primary coil, 6,000 turns, and 600 turns in the secondary coil. Yet again, this is a divide of 10. The output voltage is 12 volts. The resistor is connected to the secondary coil and dissipates 24 volts of power. Okay. What is the current in the primary coil here? So first and foremost, here to here is divided by 10, right? So here to here should be a multiply of 10, which is essentially 120 volts lah. With 120 volts, since the efficiency of the transformer is 100%, can I say that power is equals to VI, right? So I is supposed to be P over V, which is obviously going to be 24 divided by 120. If you take 24 and you divide it by 120, you're supposed to get exactly 0.2 amperes. Okay, that's why the answer is B here. Moving on to the next part, figure 10.1 shows a transformer that consists of two coils P and Q and an iron core. There are 200 turns in the primary coil and 340 turns in the secondary coil. This is obviously a step-up transformer. A 4 volts AC power supply is connected to the primary coil at P. Explain why there is a voltage between the two terminals of coil Q here, and you can see that it's 3 marks. Now in your IGCSEs, if they ever ask you something that gives you more than 2 marks, right, which is 3 or 4 marks here, it is basically asking you how the whole transformer is going to work. And for those who don't remember, I've mentioned this in class, the transformer works on the base of electromagnetic induction, right? This 4 volt AC power supply will produce alternating current in the primary coil, which will produce a alternating magnetic field in the secondary coil. This alternating magnetic field will consistently cut through the secondary coil and produce an EMF with an alternating current here as well, right? So you're supposed to put all of those in basically word lah, right? So if I were to type this out, I'll say something like AC power supply supplies alternating current the primary coil. This produces an alternating magnetic field that cuts through the secondary coil. EMF is induced in the secondary coil, produce an alternating current in the secondary coil. Yeah, so you're supposed to say something like this to get your full marks. Alright, you don't have to write it word by word, but the few keywords is definitely alternating current, producing alternating magnetic field, cutting through the secondary coil, producing an EMF, which is ultimately going to induce an alternating current. Okay? Then explain why the core of the transformer must be made of soft iron, because if you guys remember, soft iron is considered a soft metal, right? It's easy to magnetize and easy to demagnetize, which is essentially what we want for a temporary magnet. Soft iron is easy to magnetize and easy to demagnetize. It is used as a temporary magnet. Okay. Then after that, they ask you to calculate the voltage between the two terminals of coil Q here. If you have 200 turns and 340 turns here to here, yeah, I think you'll have to use the formula for this one here, right? Which is essentially voltage in the secondary over voltage in the primary is equals to number of turns in the secondary over the number of turns in the primary here, right? So you're supposed to use X over voltage primary, which is 4, is equals to number of turns 340 divided by 200 here, right? Press all of that into your calculator. 240 divided by 200 times 4. You're supposed to get a voltage of 6.8 volts, guys. 6.8 volts here. Alright. Then the heater is connected to the coil Q. The current in the heater is 3.5 amperes. The transformer is 100%. Calculate the current in coil P here. Yet again, power is 100%, means to say power in the primary coil is equals to power in the secondary coil. Voltage current is supposed to be equals to voltage current in the primary and secondary. So in here, voltage primary is 4, right? I, which is the one that we're looking for, is equals to the voltage in the secondary coil, which is 6.8, multiplied by 3.5 here. Yet again, do your simple algebra. 6.8 times 3.5 divided by 4. You're supposed to get somewhere around 5.95 amperes here, guys. 5.95 amperes here. And finally, moving to the last part here. A transformer is used to step up a voltage before the electrical energy is transmitted over long distances. State and explain one economical effects of transmitting electrical energy at high voltages. When they talk about economical benefit, you basically have to mention in terms of money, right? So my statement is, it will be cheaper to produce energy because electrical energy at high voltage will have low current. Low current in the wire produces less heat and loses less power to the surrounding. Okay? So we're supposed to say this. Alright. Then moving on to the next exercise here. The diagram shows a transformer, primary coil, blah blah blah. Which material are most suitable for the core and the coils? The core should be made of iron because it should transmit the magnetic field. The coil should be made of copper because it's easy to transfer it, energy, right? Electrical energy, right? Current or whatever lah. Okay. Then figure 10.2 shows a transformer 120 to 12 volts is step down transformer. The primary turn has 800 turns here and an input of 240 volts. The secondary turn has an output of 12 volts here. Calculate the number of turns in the secondary coil. You're supposed to use the formula yet again. Number of turns in the secondary coil over number of turns in the primary coil is equals to voltage of the secondary coil over voltage of the primary coil here. From here, it is essentially Ns over 8,000 is equals to 12 over 240. So yet again, calculator 12 divided by 240 multiplied by 8,000 here. You're supposed to get a voltage of 400, sorry, not voltage, 400 turns only. You're supposed to get 400 turns on the secondary coil. 400 turns. Okay. Then after that, explain why the voltage of the supply to the primary coil must be alternating. Now basically you have to understand that alternating current must be connected to the transformer because you want alternating magnetic field that can consistently cut through the secondary coil, guys. This is a very, very important concept that you must understand. So from here you're going to say that alternating current produces an alternating magnetic field that can keep cutting through the secondary coil, which produces EMF and alternating current in the secondary coil. Okay, you're supposed to mention something like this. right? But the keyword is always going to be because it's cutting through the secondary coil, yeah. And moving on, figure 10.1 shows a transformer, yet again somewhat similar. There are 8,000 turns in the primary coil. The primary coil is connected to 240 volts main power supply. A 6 volt lamp is connected to the secondary coil operated at full brightness. Calculate the number of turns in the secondary coil. Number of turns in the secondary coil over number of turns in the primary coil is equal to voltage S over voltage P, which is going to be Ns over 8,000 is equals to 6 over 240 yet again, right? So from here, press everything in the calculator. 6 divided by 240 multiplied by 8,000 here. You're supposed to get 200 number of turns. You're supposed to get 200 number of turns here. Then the current in the lamp is 2 amperes. The transformer operates at 100% efficiency yet again if it's 2 amperes here. Calculate the current in the primary coil. Power primary is equals to power secondary. VI is equals to VI. So it's 240 multiplied by I is equals to 6 multiplied by 2. Yet again, calculator 6 times 2 divided by 240. You're supposed to get a current of 0.05 amperes. But you're supposed to write everything in at least 2 significant figures. So it's 0.050 amperes here. Okay. Then the primary circuit contains 2 ampere fields. Calculate the maximum number of lamps identical to the lamp in one that can be connected in parallel in the secondary coil here. This one is essentially just 2 divided by 0.05, right? Because they only allow 2 amperes and if they are connected in parallel, it means to say the 0.05 is going to split, right? So it's 2 divided by 0.05 here, which if you press into the calculator, you're supposed to get 40 lamps. You're supposed to get 40 lamps here. Basically, this 2 amperes has to be split among 40 lamps that all operate on 0.05 amperes. Okay, so 40 lamps here. And finally, look at the final part here. A transformer consists of 2 coils of wire wound on a metal core. Figure 10.1 represents the transformer here. State the name of the metal from which the metal core is made of. Obviously, it's going to be iron, right? Soft iron is always going to be a standard answer here. It must be soft iron because it needs to transmit the magnetic field. The primary coil on the transformer is connected to the output voltage of an AC generator which supplies an alternating current. Explain why there is a voltage between the 2 terminals of the secondary coil. Yet again, this one here is asking us how a transformer works. You're supposed to say that AC power supply produces alternating current in the primary coil, which produces an alternating magnetic field. This alternating magnetic field cuts through the secondary coil, producing an EMF and alternating current in the secondary coil. It's quite a standard question by now. Whenever you see like 3 marks, you should be careful, and it is most likely going to ask you for the concept of how a transformer works. Okay, so moving on to the next part, there are 560 turns in the primary coil and 910 turns in the secondary coil. The voltage between the 2 terminals of the secondary coil is this. So this is Vs, this is Np, and this is Ns, right? Calculate the voltage supplied by the AC generator, which is Vp over Vs is equals to Np over Ns here. So from here, it's essentially Vp over 78 is equals to 560 divided by 910 here. Yet again, calculator 560 divided by 910 multiplied by 78. everything into the calculator, gives you a voltage of 48 volts here. 48 volts here. And finally, transformers are used to increase the voltage when the electrical energy is transmitted in cable across long distances. Explain why power loss in the cables are lower when the voltage is high. Now, basically, in this question here, they're asking about power, right? And they also mentioned, we're also told that the voltage is supposed to be high here. Yet again, the reason why we want high voltage is because we want to lower the current. When we lower the current, less friction, less heat is generated in the wire, and ultimately having less energy loss into the surrounding and less power loss. But in terms of power here, the only formula that I can think about is going to be P equals to I square R. For those who can't remember how we derive this, is basically from the P equals to VI and V equals to IR, right? We substitute this V into this V here, which will ultimately gives us P equals to IR times with I, which is ultimately P equals to I square R. Now, if we look at this equation here, increase in voltage is going to decrease the current, right? And a decrease in current is obviously going to help decrease the power loss. So you're supposed to mention something along the lines here. Oh, God. Yeah, probably want to write something like this, right? When voltage is high, current is low, right? According to the P equals to I square R formula, a decrease in current decreases the loss of power to the surrounding. Okay, and this is how you're supposed to do this question here. Finally, a last set of exercise here. Yet again, they say that the transformer is 100% efficient. If the input is 240 volts and output is 60 volts, the current in the primary coil is going to be this. So from here, first things first is I notice is a divide by 4, right? If it's a divide by 4, this here should be a multiple of 4, right? So if I multiply this by 4 here, it is essentially going to be C. If not, you can just use the VI equals to VI formula, guys. All right. A step-up transformer produces a 60 volt AC output from a 12 volt input here. There are 50 turns in the secondary coil. So it's 12 and 60, then the number of turns is 50, and you're looking for the number of turns in the primary coil here. Here to here is a multiple of 5, so here to here should be a multiple of 5 as well. So naturally it should be 10 turns. For those who are uncertain, you can always use the formula, right? And looking at the last part here, the primary coil P has 4,000 turns at an input of 120 volts. The secondary coil has 9 volts here. Calculate the number of turns in the secondary coil. So from here, since it's a paper 4 question, we'll have to do the full formula, right? Which is going to be Vs over Vp here. It's essentially going to give you something like X over 4,000 is equals to 9 over 120. And again, calculator 9 divided by 120 multiply by 4,000 here. You're supposed to get exactly 300 number of turns. You're supposed to get 300 number of turns. And finally, state the suitable material for the core of the transformer. It must be none other than a soft iron core. Okay, and that concludes the transformer chapter.